Learning objectives. In this chapter, the user will learn the following in detail. Introduction, techniques for efficient visible surface algorithms, coherence, the perspective transformation, extents and bounding volumes, backface culling, algorithms for visible line determination, Appel's algorithm, Z-buffer algorithm, depth sort algorithm, binary space partitioning tree algorithm, representing 3D data using Octrees, Boolean operations on Octrees, visible surface ray tracing. Algorithms for visible line determination. The algorithms presented here all operate in object precision and produce as output a list of visible line segments suitable for vector display. The visible surface algorithms can also be used for visible line determination by rendering each surface as a background colored interior surrounded by a border of the desired line color. Most visible surface algorithms produce an image precision array of pixels rather than an object precision list of edges. Sample algorithms for visible line determination are Roberts' algorithm, Appel's algorithm, haloed lines. Appel's algorithm. More general visible line algorithms require only that lines be the edges of polygons, not polyhedra. These algorithms also consider only lines that bound front-facing polygons and take advantage of edge coherence in a fashion typified by Appel's algorithm. Appel defines the quantitative invisibility of a point on a line as the number of front-facing polygons that obscure that point. When a line passes behind a front-facing polygon, its quantitative invisibility is incremented by 1. When it passes out from behind that polygon, its quantitative invisibility is decremented by 1. A line is visible only when its quantitative invisibility is 0. Line AB in this figure is annotated with the quantitative invisibility of each of its segments. Figure shows quantitative invisibility of a line. Dashed lines are hidden. Intersections of AB's projection with projections of contour lines are shown as large dots, and each segment of AB is marked with its quantitative invisibility. If interpenetrating polygons are not allowed, a line's quantitative invisibility changes only when it passes behind what Appel calls a contour line. A contour line is either an edge shared by a front-facing and a back-facing polygon, or the unshared edge of a front-facing polygon that is not part of a closed polyhedron. An edge shared by two front-facing polygons causes no change in visibility and therefore is not a contour line. In previous figure, edges AB, CD, DF and KL are contour lines, whereas edges CE, EF, JK are not. A contour line passes in front of the edge under consideration if it pierces the triangle formed by the eye point and the edge's two end point. Whether it does so can be determined by a point in polygon containment test. The projection of such a contour line on the edge can be found by clipping the edge against the plane determined by the eye point and the contour line. Appel's algorithm requires that all polygon edges be drawn in a consistent direction about the polygon so that the sign of the change in quantitative invisibility is determined by the sign of the cross product of the edge with the contour line. The algorithm first computes the quantitative invisibility of a seed vertex of an object by determining the number of front-facing polygons that hide it. This can be done by a brute force computation of all front-facing polygons whose intersection with the projector to the seed vertex is closer than is the seed vertex itself. The algorithm then takes advantage of edge coherence by propagating this value along the edges emanating from the point, incrementing or decrementing the value of each point at which an edge passes behind a contour line. Only sections of edges whose quantitative invisibility is 0 are drawn. When each line's other endpoint is reached, the quantitative invisibility associated with that endpoint becomes the initial quantitative invisibility of all lines emanating in turn from it. At vertices through which the contour line passes, there is a complication that requires us to make a correction when propagating the quantitative invisibility. One or more lines emanating from the vertex may be hidden by one or more front-facing polygons sharing the vertex. For example, in previous figure, edge JK has a quantitative invisibility of 0, while edge KL has a quantitative invisibility of 1 because it is hidden by the object's top face. This change in quantitative invisibility at a vertex can be taken into account by testing the edge against the front-facing polygons that share the vertex. For an algorithm such as Apple's to handle intersecting points, it is necessary to compute the intersections of an edges with front-facing polygons and to use each such intersection to increment or decrement the quantitative invisibility. Since visible line algorithms typically compare whole edges with other edges or objects, they can benefit greatly from spatial partitioning approaches. Each edge then needs to be compared with only the other edges or objects in the grid boxes containing its projection. Binary space partitioning trees. The binary space partitioning (BSP) tree algorithm is an extremely efficient method for calculating the visibility relationships among a static group of 3D polygons as seen from an arbitrary viewpoint. It trades off an initial time and space intensive preprocessing step against a linear display algorithm that is executed whenever a new viewing specification is desired. Thus, the algorithm is well suited for applications in which the viewpoint changes, but the objects do not. The BSP tree algorithm is based on the work of Schumacher, who noted that environments can be viewed as being composed of clusters, collections of faces, as shown in this figure. Clusters 1 through 3 are divided by partitioning planes P1 and P2, determining regions A through D, in which the eye point may be located. Each region has a unique cluster priority. If a plane can be found that wholly separates one set of clusters from another, then clusters that are on the same side of the plane as the eye point can obscure, but cannot be obscured by clusters on the other side. Each of these sets of clusters can be recursively subdivided if suitable separating planes can be found. As shown in this figure, this partitioning of the environment can be represented by a binary tree rooted at the first partitioning plane chosen. The tree's internal nodes are the partitioning planes. Its leaves are regions in space. Each region is associated with a unique order in which clusters can obscure one another if the viewpoint is located in that region. Determining the region in which the eye point lies involves descending the tree from the root and choosing the left or right child of an internal node by comparing the viewpoint with the plane at that node. Schumacher selects the faces in a cluster so that a priority ordering can be assigned to each face independent of the viewpoint, as shown in this figure. After backface culling has been performed relative to the viewpoint, a face with a lower priority number obscures the face with a higher number wherever the faces' projections intersect. For any pixel, the correct face to display is the highest priority, lowest numbered face in the highest priority cluster whose projection covers the pixel. Schumacher used special hardware to determine the frontmost face at each pixel. Alternatively, clusters can be displayed in order of increasing cluster priority based on the viewpoint, with each cluster's faces displayed in order of their increasing face priority. Rather than take this two-part approach to computing an order in which faces should be scan converted, the BSP tree algorithm uses a generalization of Schumacher's approach to calculating cluster priority. It is based on the observation that polygon will be scan converted correctly. That is, it will not incorrectly overlap or be incorrectly overlapped by other polygons. If all polygons on the other side of it from the viewer are scan converted first, then it and then all polygons on the same side of it as the viewer. We need to ensure that this is so for each polygon. The algorithm makes it easy to determine a correct order for scan conversion by building a binary tree of polygons, the BSP tree. The BSP tree's root is a polygon selected from those to be displayed. The algorithm works correctly no matter which is picked. The root polygon is used to partition the environment into two half spaces. One half space contains all remaining polygons in front of the root polygon, relative to its surface normal. The other contains all polygons behind the root polygon. Any polygon lying on both sides of the root polygon's plane is split by the plane and its front and back pieces are assigned to the appropriate half space. One polygon each from the root polygon's front and back half space becomes its front and back children, and each child is recursively used to divide the remaining polygons in its half space in the same fashion. The algorithm terminates when each node contains only a single polygon. The pseudocode for the tree building phase is shown in the figure. This figure shows a tree being built. Remarkably, the BSP tree may be traversed in a modified in-order tree walk to yield the correct priority ordered polygon list for an arbitrary viewpoint. Consider the root polygon. It divides the remaining polygons into two sets, each of which lies entirely on one side of the root's plane. Thus, the algorithm needs to only guarantee that the sets are displayed in the correct relative order to ensure both that one set's polygons do not interfere with the others and that the root polygon is displayed properly and in the correct order relative to the others. If the viewer is in the root polygon's front half space, then the algorithm must first display all polygons in the root's rear half space, those that could be obscured by the root, and then the root, and finally all polygons in its front half space, those that could obscure the root. Alternatively, if the viewer is in the root polygon's rear half space, then the algorithm must first display all polygons in the root's front half space, then the root, and finally all polygons in its rear half space. If the polygon is seen on edge, either display order suffices. Backface culling may be accomplished by not displaying a polygon if the eye is in its rear half space. Each of the root's children is recursively processed by this algorithm. Pseudocode for displaying a BSP tree is shown in this figure. This figure shows how the BSP tree traversed for two different projections. Projectors are shown as thin lines. White numbers indicate drawing order. Each polygon's plane equation can be transformed as it is considered, and the polygon's vertices can be transformed by the display polygon routine. The BSP tree can also assist in 3D clipping. Any polygon whose plane does not intersect the view volume has one subtree lying entirely outside of the view volume that does not need to be considered further. Which polygon is selected to serve as the root of each subtree can have a significant effect on the algorithm's performance. Ideally, the polygon selected should cause the fewest splits among all its descendants. A heuristic that is easier to satisfy is to select the polygon that splits the fewest of its children. Experience shows that testing just a few, 5 or 6 polygons and picking the best provides a good approximation to the best case. Like the depth sort algorithm, the BSP tree algorithm performs intersection and sorting entirely at object precision, relies on the image precision override capabilities of a raster device. Unlike depth sort, it performs all polygon splitting during pre-processing step that must be repeated only when the environment changes. Note that more polygon splitting may occur than in the depth sort algorithm. List priority algorithms allow the use of hardware polygon scan converters that are typically much faster than are those that check the Z each pixel. The depth sort and the BSP tree algorithms display polygons in a back-to-front order, possibly obscuring more distant ones later. Thus, like the Z buffer algorithm, shading calculations may be computed more than once for each pixel. Alternatively, polygons can instead be displayed in a front-to-back order, and each pixel in a polygon can be written only if it has not yet been. If a list priority algorithm is used for hidden line removal, special attention must be paid to the new edges introduced by the subdivision process. If these edges are scan converted like the original polygon edges, they will appear in the picture as unwelcome artifacts, and they thus should be flagged so that they will not be scan converted. Boolean operations on Octrees. Boolean set operations and transformations. Much work has been done on developing efficient algorithms for storing and processing quadtrees and octrees. For example, Boolean set operations are straightforward for both quadtrees and octrees. To compute the union or intersection U of the two trees, S and T, we traverse both the trees top-down in parallel. This figure shows the operations for quad trees. The generalization to octrees is straightforward. Each matching pair of nodes is examined. Consider the case of union. If either of the nodes in the pair is black, then a corresponding black node is added to U. If one of the pair's nodes is white, then the corresponding node is created in U with the value of the other node in the pair. If both nodes of the pair are gray, then a gray node is added to U and the algorithm is applied recursively to the pair's children. In this last case, the children of the new node in U must be inspected after the algorithm has been applied to them. If they are all black, they are deleted and their parent in U is changed from gray to black. The algorithm for performing intersection is similar, except the roles of black and white are interchanged. If either of the nodes in a pair is white, then a corresponding white node is added to U. If one of the pair's nodes is black, then the corresponding node is created in U with the value of the other node in the pair. If both nodes of the pair are gray, then a gray node is added to U and the algorithm is applied recursively to the pair's children. As in the union algorithm, if both nodes are gray, then after the algorithm has been applied to the children of the new node in U, the children must be inspected. In this case, if they are all white, they are deleted and their parent in U must be changed from gray to white. It is easy to perform simple transformations on quad trees and octrees. For example, rotation about an axis by multiples of 90 degrees is accomplished by recursively rotating the children at each level. Scaling by powers of 2 and reflections are also straightforward. Translations are somewhat more complex, as are general transformations. In addition, as in spatial occupancy enumeration in general, the problem of aliasing under general transformations is severe. Depth sort algorithm. The basic idea of the depth sort algorithm is to paint the polygons into the frame buffer in order of decreasing distance from the viewpoint. 3 conceptual steps are performed. 1. Sort all polygons according to the smallest, farthest z coordinate of each. 2. Resolve any ambiguities that may cause, when the polygon z extends, overlap, splitting polygons if necessary. 3. Scan convert each polygon in ascending order of smallest z coordinate back to front. Consider the use of explicit priority such as that associated with use in SFIGS, Simple Programmer's Hierarchical Graphics Standard. The explicit priority takes the place of the minimum z value, and there can be no depth ambiguities because each priority is thought of as corresponding to a different plane of the constant z. This simplified version of the depth sort algorithm is often known as the painter's algorithm, in reference to how a painter might paint closer objects over more distant ones. Environments whose objects each exist in a plane of constant z, such as those of VLSI layout, cartography and window management, are said to be 2.5D and can be correctly handled with the painter's algorithm. The painter's algorithm may be applied to a scene in which each polygon is not embedded in a plane of constant z by sorting the polygons by their minimum z coordinate or by the z coordinate of their centroid, ignoring step 2. Although scenes can be constructed for which this approach works, it does not in general produce a correct ordering. This figure shows some of the types of ambiguities that must be resolved as part of step 2. How is this done? Let the polygon currently at the far end of the sorted list of polygons be called P. Before this polygon is scan converted into the frame buffer, it must be tested against each polygon Q, whose z extent overlaps the z extent of P, to prove that P cannot obscure Q, and that P can therefore be written before Q. Up to 5 tests are performed in order of increasing complexity. As soon as one succeeds, P has been shown not to obscure Q, and the next polygon Q overlapping P in Z is tested. If all such polygons pass, then P is scan converted and the next polygon on the list becomes the new P. The 5 tests are: do the polygons X extents not overlap? Do the polygons Y extents not overlap? Is P entirely on the opposite side of Q's plane from the viewpoint? Is Q entirely on the same side of P's plane as the viewpoint? Do the projections of the polygons onto the xy plane not overlap? This can be determined by comparing the edges of one polygon to the edges of the other. If all 5 tests fail, we assume for the moment that P actually obscures Q and therefore test whether Q can be scan converted before P. Tests 1, 2 and 5 do not need to be repeated, but new versions of tests 3 and 4 are used with the polygons reversed. 3 dash. Is Q entirely on the opposite side of P's plane from the viewpoint? 4 dash. Is P entirely on the same side of Q's plane as a viewpoint? In the case of figure A, test 3 dash succeeds. Therefore, we move to Q to the end of the list and it becomes a new P. In the case of figure B, the tests are still inconclusive. In fact, there is no order in which P and Q can scan converted correctly. Instead, either P or Q must be split by the plane of the other. The original unsplit polygon is discarded, its pieces are inserted in the list in proper Z order, and the algorithm proceeds as before. The figure C shows a more subtle case. It is possible for P, Q and R to be oriented such that each polygon can always be moved to the end of the list to place it in the correct order relative to one, but not both of the other polygons. This would result in an infinite loop. To avoid looping, we must modify our approach by marking each polygon that is moved to the end of the list. Then whenever the first 5 tests fail and the current polygon Q is marked, we do not try tests 3 dash and 4 dash. Instead, we split either P or Q as if tests 3 dash and 4 dash had both failed and reinsert the pieces. Can 2 polygons fail all the tests even when they are already ordered correctly? Consider P and Q as shown in this figure. Only the Z coordinate of each vertex is shown. With P and Q in their current position, both the simple painter's algorithm and the full depth sort algorithm scan convert P first. Now rotate the Q clockwise in its plane until it begins to obscure P, but do not allow P and Q themselves to intersect as shown in figure B. P and Q have overlapping Z extents, so they must be compared. Note that tests 1 and 2, X and Y extent, fail. Tests 3 and 4 fail, because neither is wholly in one half space of the other, and test 5 fails because the projections overlap. Since tests 3 dash and 4 dash also fail, a polygon will be split even though P can be scan converted before Q. Although the simple painter's algorithm would correctly draw P first because P has the smallest minimum Z coordinate, try the example again with Z equals minus 0.5 at P's bottom and Z equals 0.5 at P's top. Introduction. Given a set of 3D objects and a viewing specification, we wish to determine which lines or surfaces of the objects are visible, either from the center of projection for perspective projections or along the direction of projection for parallel projections, so that we can display only the visible lines or surfaces. This process is known as visible line or visible surface determination, or hidden line or hidden surface elimination. In visible line determination, lines are assumed to be the edges of opaque surfaces that may obscure the edges of other surfaces farther from the viewer. Therefore, we shall refer to the general process as visible surface determination. This fundamental idea is simple, but its implementation requires significant processing power and consequently involves large amounts of computer time on conventional machines. These requirements have encouraged the development of numerous carefully structured visible surface algorithms. The first approach determines which of n objects is visible at each pixel in the image. The pseudocode for this approach looks like this. A straightforward brute force way of doing this for one pixel requires examining all n objects to determine which is closest to the viewer along the projector passing through the pixel. For p pixels, the effort is proportional to np, where p is over 1 million for a high-resolution display. The second approach is to compare objects directly with each other, eliminating entire objects or portions of them that are not visible. Expressed in pseudocode, this becomes as shown on the screen. In second approach, Individual steps are typically more complex and time-consuming, so it is often slower and more difficult to implement. We refer to these prototypical approaches as image precision and object precision algorithms, respectively. Image precision algorithms are typically performed at the resolution of the display device and determine the visibility at each pixel. Object precision algorithms are performed at the precision with which each object is defined and determine the visibility of each object. Object precision algorithms were first developed for vector graphic systems. On these devices, hidden line removal was most naturally accomplished by turning the initial list of lines into one in which lines totally hidden by other surfaces were removed and partially hidden lines were clipped to one or more visible line segments. Vector displays had a large address space and severe limits on the number of lines and objects that could be displayed. Raster displays, on the other hand, had a limited address space and the ability to display a potentially unbounded number of objects. Later, algorithms often combine both object and image precision calculations, with object precision calculations chosen for accuracy and image precision chosen for speed. Functions of two variables. One of the most common uses of computer graphics has been to plot single-valued continuous functions of two variables such as y equals function of x and z. These functions define surfaces like that shown in this figure. They present an interesting special case of the hidden surface problem, for which especially fast solutions are possible. A function of x and z may be approximated by an m by n array y of values. Each array element may be thought of as representing a height at one point in a regular grid of samples. We assume that each column of the array corresponds to a single x coordinate and that each row of the array corresponds to a single z coordinate. In other words, the rectangular array is aligned with the x and z axes. The indices of an array element and the element's value together specify the coordinates of a 3D point. A wireframe drawing of the surface may be constructed as a piecewise linear approximation by drawing one set of polylines through the points defined by each row of the array y, polylines of constant z, and an orthogonal set of polylines through the points defined by each column, polylines of constant x. A hidden line algorithm must suppress all pans of the lines that would be obscured from the viewpoint by other parts of the surface as shown in this figure. To see how we might accomplish this, first consider the problem of plotting only polylines of constant z, assuming that the closest polyline to the viewpoint is an edge of the surface. An efficient class of solutions to this problem is based on the recognition that each polyline of constant z lies in a separate parallel plane of constant z. Since none of these planes, and hence none of the polylines, can intersect any of the others, each polyline cannot be obscured by any polyline of constant z farther from the viewpoint. Therefore, we will draw polylines of constant z in order of increasing distance from the viewpoint. This establishes a front-to-back order. Drawing each polyline of constant z correctly requires only that we not draw those parts of the polyline that are obscured by parts of the surface already drawn. Consider the silhouette boundary of the polylines drawn thus far on the view plane, shown as thick lines in this figure. When a new polyline is drawn, it should be visible only where its projection rises above the top or dips below the bottom of the old silhouette. Since each new polyline has a constant z that is farther than that of any of the preceding polylines, it cannot pierce any part of the surface already drawn. Therefore, to determine what parts are to be drawn, we need only to compare the current polyline's projected y values, with those of the corresponding part of the surface's silhouette computed thus far. When only enough information is encoded to represent a minimum and maximum silhouette y for each x, the algorithm is known as the horizon line algorithm. One way to represent this silhouette uses the two 1D arrays ymin and ymax to hold the minimum and maximum projected y values for a finite set of projected x values. These are image precision data structures because they have a finite number of entries. Ymin and Ymax are initialized with Y values that are respectively above and below all the projected Y values of the surface. When a new polyline is drawn, the projected Y values of each pair of adjacent vertices are compared with the values at the corresponding locations in the silhouette arrays. As shown in this figure, a vertex whose value is above that in the corresponding position in Ymax A, B, G or below that in Ymin E, F is visible. Otherwise, it is invisible. C, D. If both vertices are invisible, then the line segment is wholly invisible, CD, and the silhouette arrays remain unchanged. If both vertices are visible with regard to the same silhouette array, AB, EF, then the line segment is wholly visible and should be drawn in its entirety, and that silhouette array should be updated. The x-coordinates of two adjacent vertices in a polyline of constant z usually map to non-adjacent locations in the silhouette arrays. In this situation, values of y, twins in the intervening silhouette array locations, can be obtained by linearly interpolating between the projected y values of the two adjacent elements of y. Finally, we must consider the case of a partially visible line, in which both vertices are not visible with regard to the same silhouette array. Although this typically means that one of the vertices is visible and the other is invisible, BC, DE, it may be the case that both vertices are visible, one above Ymax and the other below Ymin, FG. Interpolated Y values can be compared with those of the intervening locations in the silhouette arrays to determine the points of intersection. The line should not be visible at those places where an interpolated Y value falls inside the silhouette. Only the visible parts of the line segment outside the silhouette should be drawn, and the silhouette array should be updated as shown in the above figure. When the two adjacent silhouette elements are found between which the line changes visibility, the line can be intersected with the line defined by the x and y values of those elements to determine an endpoint for a line drawing algorithm. Drawback of the image precision Ymin and Ymax silhouette arrays is that it leads to aliasing problems. If the line drawing primitive used has higher resolution than do the silhouette arrays, aliasing can manifest itself as hidden segments that are drawn or as visible segments that are not. For example, this figure shows three polylines being drawn in front to back order. The two polylines of paths A and B form a gap when they cross. The second line can be correctly hidden by the first by interpolating the values in Ymax to determine the intersection of these two lines. After the second line has been drawn, however, both values in Ymax are the same, so that the third line drawn in path C incorrectly remains hidden when it passes over their intersection. Using higher resolution silhouette arrays can reduce such problems at the expense of increased processing time. An alternative to image precision Ymin and Ymax arrays is to use object precision data structures. The Ymin and Ymax arrays can be replaced by two object precision polylines representing the silhouette boundaries. As each segment of a polyline of constant z is inspected, only those parts projecting above the Ymax polyline or below the Ymin polyline are drawn. The projected lines representing these visible parts are linked into the silhouette polyline beginning at the point at which they intersected, replacing the subsequent parts of the silhouette polyline until the next intersection. The accuracy gained by this approach must be weighed against the extra runtime overhead incurred by searching and maintaining the silhouette polylines and the added difficulties of coding a more complex algorithm. Suppose we wish to draw polylines of constant x instead of polylines of constant z to produce a view shown in this figure. In this case, the polyline of constant x closest to the observer does not form an edge of the surface. It is the seventh, the most nearly vertical polyline from the left. To render the surface correctly, we must render polylines to the right of the closest one from left to right, and those to the left of the closest one from right to left. In both cases, polylines are rendered in front-to-back order relative to the observer. The image precision algorithm can be easily extended to plot lines of constant x as well as of constant z, as shown in the figure. Although it is tempting to assume that superimposing the correctly plotted polylines of constant x and polylines of constant z would work, this does not allow lines from each set to hide those in the other, as shown in the figure. The correct solution can be obtained by interleaving the processing of the two sets of polylines. The set of those polylines that are most nearly parallel to the view plane, that is, those of the constant z, is processed in the same order as before. After each polyline of constant z is processed, the segments of each polyline of constant x between the just processed polyline of z and the next polyline of z are drawn. The line segments of x must be drawn using the same copy of the silhouette data structure as that was used for drawing the polylines of constant z. In addition, they too must be processed in front-to-back order. This figure shows the lines of constant x as processed in the correct order, from left to right in this case. The lines of constant x in this figure have been processed in the opposite incorrect order, from right to left. The incorrect drawing order causes problems because each successive line is shadowed in the Y-max array by the lines drawn previously. Although the algorithms are both useful and efficient, they fail for any viewing specification for which the silhouette of the object is not a function of x when projected on the view plane. An example of such a viewing specification is shown in this figure, which was rendered with an algorithm developed by Anderson that uses more complex data structures to handle arbitrary viewing specifications. Solved problems. Why are hidden surface algorithms needed? Hidden surface algorithms are needed to determine which objects in surface will obscure those objects in surfaces that are at the back, thus rendering a more realistic image. What two steps are required to determine whether any given point P1, x1, y1, z1 obscures another point P2, x2, y2, z2? It must be determined whether the 2 points lie on the same projection line, and if they do, which point is in front of the other. Why is it easier to locate hidden surface when parallel projection is used? There are no vanishing points in parallel projection. As a result, any point P, A, B, Z will lie on the same projector as any other point having the same x and y coordinates, A, B. Thus, only the z component must be compared to determine which point is closest to the viewer. Representing 3D data using Octrees. Algorithms for displaying Octree-encoded objects take advantage of the Octrees regular structure of non-intersecting cubes. Since the Octree is spatially pre-sorted, list priority algorithms have been developed that yield a correct display order for parallel projections. In a back-to-front enumeration, nodes are listed in an order in which any node is guaranteed not to obscure any node listed after it. For an orthographic projection, a correct back-to-front enumeration can be determined from the VPN alone. One approach is to display the farthest octant first, then those three neighbors that share a face with the farthest octant in any order, then those three neighbors of the closest octant in any order, then the closest octant. In this figure, one such enumeration for VPN from 0 to V is 0, 1, 2, 4, 3, 5, 6, 7. No node in this enumeration can obscure any node enumerated after it. As each octant is displayed, its descendants are displayed recursively in this order. Furthermore, because each leaf node is a cube, at most 3 of its faces are visible, the identities of which may also be determined from the VPN. A positive or negative VPN x-coordinate means the right R or left L face is visible respectively. Similarly, the y-coordinate determines the visibility of the up U and down D faces, and the z-coordinate controls the front F and back B faces. If any VPN coordinate is 0, then neither of the faces associated with it is visible. Only the VPN's non-zero coordinates are significant in determining an order. Since all Octree nodes are identically oriented, the visible faces and their relative polygonal projections for all nodes need to be determined only once. Arbitrary parallel projections can be accommodated by considering the DOP instead of the VPN. Another approach to back-to-front enumeration for orthographic projections iterates through the octants in slices perpendicular to one of the axes and in either rows or columns within each slice. The sign of each component of the VPN determines the direction of iteration along the corresponding octree axis. A positive component indicates increasing order along its axis, whereas a negative component indicates decreasing order. The order in which the axes are used does not matter. This approach is easily generalized to operate on voxel arrays. It is not necessary to display all an object's voxels, since those that are surrounded entirely by others will ultimately be invisible. More efficient scan conversion can be accomplished by rendering only the voxels on the Octrees border. Meager describes a front-to-back algorithm that uses the reverse of the back-to-front order described previously. It represents the image being rendered as a quad tree that is initially empty. Each full or partially full Octree node is considered in front-to-back order and is compared with the quadtree nodes that its projection intersects. Those Octree nodes whose projections intersect only full quadtree nodes are invisible. They and their descendants are not considered further. If a partially full Octree node's projection intersects one or more partially full quadtree nodes, then the Octree's node children are compared with the children of these quadtree nodes. If a full Octree node's projection intersects partially full quadtree nodes, then only the partially full tree nodes are further subdivided to determine the previously empty nodes that are covered by the projection. Any empty quadtree node enclosed by a full Octree node's projection is shaded with the Octree node's value. As shown in this figure, Meager bounds each Octree node projection with an upright rectangular extent. Front-to-back Octree scan conversion. Each Octree node's projection and the rectangular extent are compared with the four quadtree nodes, here 12, 13, 30 and 31. Any extent needs to be compared with only four of the lowest level quadtree nodes, whose edge size is at least as great as the extent's largest dimension. These are the quadtree node containing the extent's lower left corner and the three adjacent quadtree nodes in the N, E and NE directions. For example, these are quadtree nodes 12, 13, 30 and 31. If the rectangular extent intersects a rectangular quadtree node, then whether the Octree node's projection, a convex polygon, also intersects the quadtree node can be determined efficiently. In contrast to the list priority back-to-front algorithms, this front-to-back algorithm operates at an image precision because it relies on an image precision quadtree representation of the projections on the image plane. Techniques for efficient visible surface algorithms. Need for visible surface algorithms. The simple formulations of image precision and object precision algorithms require a number of costly operations. These include determining for a projector and an object or for two objects' projections whether or not they intersect and where they intersect. Then for each set of intersections, it is necessary to compute the object that is closest to the viewer and therefore visible. To minimize the time that it takes to create a picture, we must organize visible surface algorithms so that costly operations are performed as efficiently and as infrequently as possible. Some general techniques for efficient visible surface algorithms: coherence, perspective transformation, extents and bounding volumes, backculling. Coherence. Sutherland, Prowl and Schumacher point out how visible surface algorithms can take advantage of coherence, the degree to which parts of an environment or its projection exhibit local similarities. Environments typically contain objects whose properties vary smoothly from one part to another. In fact, it is the less frequent discontinuities in properties, such as depth, color, and texture, and the effects that they produce in pictures that let us distinguish between objects. We exploit coherence when we reuse calculations made for one part of the environment or picture for other nearby parts, either without changes or with incremental changes that are more efficient to make than recalculating the information from scratch. Kinds of coherence are object coherence. If one object is entirely separate from another, comparisons may need to be done only between the two objects and not between their component faces or edges. For example, if all parts of object A are farther from the viewer than are all parts of object B, none of A's faces need to be compared with B's faces to determine whether they obscure B's faces. Face coherence. Surface properties typically vary smoothly across a face, allowing computations for one part of a face to be modified incrementally to apply to adjacent parts. In some models, faces can be guaranteed not to interpenetrate. Edge coherence. An edge may change visibility only where it crosses behind a visible edge or penetrates a visible face. Implied edge coherence. If one planar face penetrates another, their line of intersection, the implied edge, can be determined from 2 points of intersection. Scanline coherence. The set of visible object spans determined for one scan line of an image typically differs little from the set on the previous line. Area coherence. A group of adjacent pixels is often covered by the same visible face. A special case of area coherence is span coherence, which refers to a face's visibility over a span of adjacent pixels on a scan line. Depth coherence. Adjacent parts of the same surface are typically close in depth, whereas different surfaces at the same screen location are typically separated farther in depth. Once the depth at one point of the surface is calculated, the depth of points on the rest of the surface can often be determined by a simple difference equation. Frame coherence. Pictures of the same environment at two successive points in time are likely to be quite similar despite small changes in objects and viewpoint. Calculations made for one picture can be reused for the next in a sequence. Solved problems. How does edge coherence help to reduce computational effort? It is based on the assumption that if an edge or line intersects a given scan line, it will most likely intersect the scan lines next to it. Thus, if the pixels that intersect the edge are to be found, instead of intersecting each scan line with the edge, it is sufficient to locate only one intersection pixel and then find others using the slope m of the edge as shown here. 2. How does area coherence reduce computational effort? Area coherence is based on the assumption that a small enough region of pixels will most likely lie within a single polygon. This reduces, as in the subdivision algorithm, computational effort in dealing with all those polygons that are potentially visible in a given screen area, region of pixels. The perspective transformation. Visible surface determination clearly must be done in a 3D space prior to the projection into 2D that destroys the depth information needed for depth comparisons. Regardless of the kind of projection chosen, the basic depth comparison at a point can be typically reduced to the following question. Given points P1, x1, y1, z1, and P2, x2, y2, z2, does either point obscure the other? This question is the same. Are P1 and P2 on the same projector? If the answer is yes, z1 and z2 are compared to determine which point is closer to the viewer. If the answer is no, then neither point can obscure the other. Depth comparisons are typically done after the normalizing transformation has been applied, so that the projectors are parallel to the z-axis in parallel projections or emanate from the origin in perspective projections. For a parallel projection, the points are on the same projector if x1 equals x2 and y1 equals y2. For a perspective projection, we must perform 4 divisions to determine whether x1 by z1 equals x2 by z2 and y1 by z1 equals y2 by z2, in which case the points are on the same projector as shown in this figure. Moreover, if P1 is later compared against some P3, 2 more divisions are required. Unnecessary divisions can be avoided by first transforming a 3D object into a 3D screen coordinate system so that the parallel projection of the transformed object is the same as the perspective projection of the untransformed object. Then the test for one point obscuring another is the same as for parallel projections. This perspective transformation distorts the objects and moves the center of projection to infinity on the positive z-axis, making the projectors parallel. This figure shows the effect of this transformation on the perspective view volume. The normalized perspective view volume A before and B after perspective transformation. This figure shows how a cube is distorted by the transformation. A cube A before and B after perspective transformation. The essence of such a transformation is that it preserves relative depth, straight lines, and planes, and at the same time performs the perspective foreshortening. The division that accomplishes the foreshortening is done just once per point rather than each time 2 points are compared. The matrix shown transforms the normalized perspective view volume into the rectangular parallelepiped bounded by x lying between or equal to -1 and 1, y lying between or equal to -1 and 1, z lying between or equal to -1 and 0. Clipping can be done against a normalized truncated pyramid view volume before m is applied, but then the clipped results must be multiplied by m. A more attractive alternative is to incorporate m into the perspective normalizing transformation, n per, so that just a single matrix multiplication is needed, and then to clip in homogeneous coordinates prior to the division. If we call the results of that multiplication x, y, z, w, then for w greater than 0, the clipping limits become x lying between or equal to -w and w, y lying between or equal to -w and w, z lying between or equal to -w and 0. These limits are derived by replacing x, y, and z by x by w, y by w, and z by w respectively to reflect the fact that x, y, and z result from division by w. After clipping, we divide by w to obtain xp, yp, and zp. Note that m assumes the view volume in the negative z half space. For notational convenience, however, our examples will often use decreasing positive z values rather than decreasing negative z values to indicate increasing distance from the viewer. In contrast, many graphics systems transform the right-handed world into the left-handed viewing coordinate system, in which increasing positive z values correspond to increasing distance from the viewer. When a parallel projection is specified, the perspective transformation m is unnecessary because the normalizing transformation n par for parallel projections makes the projectors parallel to the z-axis. Extents and bounding volumes. This figure shows two objects, 3D polygons in this case, their projections, and the upright rectangular screen extends surrounding the projections. The objects are assumed to have been transformed by the perspective transformation matrix M. Therefore, for polygons, orthographic projection onto the xy plane is done trivially by ignoring each vertex's z-coordinate. In the above figure, the extents do not overlap, so the projections do not need to be tested for overlap with one another. If the extents overlap, one of the two cases occurs, as shown in this figure. Either the projections also overlap, as in part A, or they do not, as in part B. In both cases, more comparisons must be performed to determine whether the projections overlap. In part B, the comparisons will establish that the two projections really do not intersect. In a sense, the overlap of the extents was a false alarm. Extent testing thus provides a service similar to that of trivial reject testing in clipping. Rectangular extent testing is also known as bounding box testing. Extents can be used to surround the objects themselves rather than their projections. In this case, the extents become solids and are also known as bounding volumes. Alternatively, extents can be used to bound a single dimension in order to determine, say, whether or not two objects overlap in Z. This figure shows the use of extents in such a case. Here an extent is the infinite volume bounded by the minimum and maximum Z values for each object. There is no overlap in Z if Zmax2 is less than Zmin1 or Zmax1 is less than Zmin2. Comparing against minimum and maximum bounds in one or more dimensions is also known as min-max testing. When comparing min-max extents, the most complicated part of the job is finding the extent itself. For polygons or for other objects that are wholly contained within the convex hull of a set of defining points, an extent may be computed by iterating through the list of point coordinates and recording the largest and smallest values for each coordinate. Extents and bounding volumes are used not only to compare the two objects or their projections with each other, but also to determine whether or not a projector intersects an object. This involves computing the intersection point with a 2D projection or a vector with a 3D object. Although we have discussed only min-max elements so far, other bounding volumes are possible. What is the best bounding volume to use? Not surprisingly, the answer depends on both the expense of performing tests on the bounding volume itself and on how well the volume protects the enclosed object from tests that do not yield an intersection. Weghorst, Hooper, and Greenberg treat bounding volume selection as a matter of minimizing the total cost function T of the intersection test for an object. This may be expressed as T equals B into capital B plus O into capital O, where B is the number of times the bounding volume is tested for intersection. Capital B is the cost of performing an intersection test on the bounding volume. O is the number of times the object is tested for intersection, the number of times the bounding volume is actually intersected, and capital O is the cost of performing an intersection test on the object. Since the object intersection test is performed only when the bounding volume is actually intersected, O is less than or equal to B. Although O and B are constant for a particular object and set of tests to be performed, B and O vary as a function of the bounding volume's shape and size. A tighter bounding volume, which minimizes O, is typically associated with a greater B. A bounding volume's effectiveness may also depend on object orientation or the kind of objects with which that object will be intersected. Compare the two bounding volumes for the wagon wheel shown in the figure. Bounding volume selection. If the object is to be intersected with projectors perpendicular to the x-y plane, then the tighter bounding volume is the sphere. If projectors are perpendicular to the xz or yz planes, then the rectangular extent is the tighter bounding volume. Therefore, multiple bounding volumes may be associated with an object and an appropriate one selected depending on the circumstances. Backface culling. If an object is approximated by a solid polyhedron, then its polygonal faces completely enclose its volume. Assume that all the polygons have been defined such that their surface normals point out of their polyhedron. If none of the polyhedron's interior is exposed by the front clipping plane, then those polygons whose surface normals point away from the observer lie on a part of the polyhedron whose visibility is completely blocked by other closer polygons as shown in this figure. Figure shows backface culling. Back-facing polygons A, B, D, F shown in gray are eliminated, whereas front-facing polygons C, E, G, H are retained. Such invisible back-facing polygons can be eliminated from further processing, a technique known as backface culling. By analogy, those polygons that are not back-facing are often called front-facing. In I coordinates, a back-facing polygon may be identified by a non-negative dot product, that is, surface normal forms with the vector from the center of projection to any point on the polygon. Strictly speaking, the dot product is positive for a back-facing polygon. A zero dot product indicates a polygon being viewed on edge. Assuming that the perspective transformation has been performed, or that an orthographic projection onto the xy plane is desired, then the direction of projection is 0, 0, -1. In this case, the dot product test reduces to selecting a polygon as back-facing only if its surface normal has negative z coordinate. If the environment consists of a single convex polyhedron, backface culling is the only visible surface calculation that needs to be performed. Otherwise, there may be front-facing polygons, such as C and E in the above figure, that are partially or totally obscured. If the polyhedra have missing or clipped front faces, or if the polygons are not polyhedra at all, then back-facing polygons may still be given special treatment. If culling is not desired, the simplest approach is to treat a back-facing polygon as though it were front-facing. flipping its normal in the opposite direction. In Fix Plus, the user can specify a completely separate set of properties for each side of a surface. In 2's parity check algorithm for determining whether a point is contained in a polygon, note that a projector passing through a polyhedron intersects the same number of back-facing polygons as of front-facing ones. Thus, a point in a polyhedron's projection lies in the projections of as many back-facing polygons as front-facing ones. Backface culling, therefore, halves the number of polygons to be considered for each pixel in an image precision visible surface algorithm. On average, approximately one-half of a polyhedron's polygons are back-facing. Thus, backface culling also typically halves the number of polygons to be considered by the remainder of an object precision visible surface algorithm. Note, however, that this is true only on average. For example, a pyramid's base may be that object's only back or front-facing polygon. As described so far, backface culling is an object precision technique that requires time linear in the number of polygons. Sublinear performance can be obtained by pre-processing the objects to be displayed. For example, consider a cube centered about the origin of its own object coordinate system, with its faces perpendicular to the coordinate system's axes. From any viewpoint outside the cube, at most 3 of its faces are visible. Furthermore, each octant of the cube's coordinate system is associated with a specific set of 3 potentially visible faces. Therefore, the position of the viewpoint relative to the cube's coordinate system can be used to select one of the 8 sets of 3 potentially visible faces. For objects with a relatively small number of faces, a table may be made up in advance to allow visible surface determination without processing all the object's faces for each change of viewpoint. A table of visible faces indexed by viewpoint equivalence class may be quite large, however, for an object with many faces. A graph is constructed with a node for each face of a convex polyhedron and a graph edge connecting each pair of nodes whose faces share a polygon edge. The list of edges separating the visible faces from invisible ones is then computed for an initial viewpoint. This list contains all edges on the object's silhouette. Visible surface ray tracing. Ray tracing, also known as ray casting, determines the visibility of surfaces by tracing imaginary rays of light from the viewer's eye to the objects in the scene. As center of projection, the viewer's eye and a window on an arbitrary view plane are selected. The window may be thought of as being divided into a regular grid whose elements correspond to pixels at the desired resolution. Then for each pixel in the window, an eye ray is fired from the center of projection through the pixel center to the scene, as shown in this figure. This figure shows a ray being fired from the center of projection through each pixel to which the window maps to determine the closest object intersected. The pixel's color is set to that of the object at the closest point of intersection. The pseudocode for this simple ray tracer is shown in this figure. Ray tracing was first developed by Apple and by Goldstein and Nagel. Apple used a sparse grid of rays used to determine shading, including whether a point was in shadow. Goldstein and Nagel originally used their algorithm to simulate the trajectories of ballistic projectiles and nuclear particles. Only later did they apply it to graphics. Apple was the first to ray trace shadows, whereas Goldstein and Nagel pioneered the use of ray tracing to evaluate Boolean set operations. Whitted and Kay extended ray tracing to handle specular reflection and refraction. Conclusion. In this chapter, we have covered the following in detail. Introduction, techniques for efficient visible surface algorithms, coherence, the perspective transformation, extents and bounding volumes, backface culling, algorithms for visible line determination, Apple's algorithm, Z-buffer algorithm, depth sort algorithm, binary space partitioning tree algorithm, representing 3D data using Octrees, Boolean operations on Octrees, visible surface ray tracing.